heat our home, and you can do so at a very high efficiency compared to electric resistance heaters like a space heater. If you looked at the cycle of how that happens, you have a cold reservoir, hot reservoir, and you cheat by taking heat out of the cold reservoir so you can add heat to your room, free heat, in addition to the electric power that you put in. Today we'll talk more about how do we actually run energy analysis for a building for a whole year, and how do we size the components, so how large does the heat pump have to be effective for a specific building. And then at the end we'll talk about building codes to see how building codes regulate what we can or cannot do in buildings. But first let me correct another mistake I made last time. So we looked at the COP and the EER. So EER is the energy efficiency ratio. And then we said that the COP is the coefficient of performance. That tells us what the efficiency is. That was usually around 3 or so 300% efficient. But then the factor to convert between those two is 3.4 BTU per watt hour. So last time I told you it's 3.4 BTU per kilowatt hour. That was incorrect. Apologies. It's 3.4 BTU per watt hour. That's the correct conversion factor to get from watt hours to BTU. And then your ER units, as a result, are also BTU per watt hour. So let's talk about sizing methods for HVAC. Okay, so a new building is built, or your building doesn't have AC yet. You're buying an AC for your building. How do you think we should go about sizing that AC unit for a new building or a building that doesn't have one yet? What do you think would be important for that analysis?
Anticipated heat gain.
Anticipated heat gain, right? So you want to figure out, let's talk about the cooling season. So we have hot weather outside. You want to figure out, well, how much heat is coming inside. That's the heat we have to put back outside. So if that heat is large, you need a large AC. If that heat is small, you need a small AC. Yep. Yep.
You need to know the volume of air that you have to move inside the house, because then you know how much energy you have to put into it to change the temperature.
You need to know the volume of air inside the house, and the mass of that air, because if you want to heat up your house quickly, then really you're worried about how much is the temperature of the air right now. And I want to, let's go back to cooling, want to cool it down quickly. Say in 10 minutes, I want to be sitting on the couch and not sweating anymore. Then your AC needs to be bigger because it needs more power to cool that air down very quickly.
Sorry, I have a question. Is this for like commercial buildings or a home where it's only measured in like one spot? Or like the temperature special?
Yeah, so the question was, is it commercial or home? Let's talk about home buildings for now.
So I would say the location for where you're measuring the heat, do you know, like, similar to what he's saying, like kind of what the heat gradient looks like within the home, so you can choose a good spot to actually measure it from?
Yeah, you want to worry about location of where you put it, right? So especially if you have a window unit, then you know it's going to be coolest right in that room where the window unit is. The further you move away from it, the warmer it will get. So you want to put the unit into a place where you would be most of the time you want it to be cool. So you would put the AC in the bedroom if you like it cool at night, or even put it in the living room if you like it cool in the living room. So you have options about locations too. Yep.
Another thing is you need to know how fast the house is heating up. So if you have really poor insulation or lots of like cracks and stuff in the doors, if heat's coming in constantly, it doesn't matter how much air you have in the house that you need to cool if it can't keep up.
Yeah, so you know about how fast the house is heating up, so how much heat is coming in from the outside. That's the important design factor. But let's think about we know that how much heat comes in depends on the weather conditions outside, right? So what should we use? What conditions should we use to size the system? Should we use, so again, talk about cooling, so hot conditions. Should we use the average summer day? Should we use a hot summer day, cooler summer day? What's the right day we should use to size the system?
Depends how much money you have.
The average summer temperature?
We use the average summer temperature, right? So that would be one option. That means that on average, if you have an average day, we would be having the house nice and cool. What would happen on a hot day then?
You know, sweat it out.
On a hot day, you have to sweat it out, right? Because on a hot day, your system won't be large enough, so it actually can't keep up. There's too much heat is coming in because your delta T, outside, inside, is too large. So more heat is coming in through conduction, through infiltration. And now your AC is too small. It's not sized big enough to remove all that heat, which means you can still cool it compared to the outside, but you're now maybe exceeding your comfort level. So you're sweating it out. You have to go to UCSD, to the library, for a few weeks, right? So do you think that's what people do? Do you think people size system based on the average temperature?
I don't think
No?
so.
Okay. What else do they do?
Assuming that they have a system that can like have variable power outputs, you would just take whatever kind of you expect to be the most you need out of it, so that you can vary it day by day.
Yeah, so you would size the system to what you think the most would be that you would take out of it, right? Now let's think about that example. So the most, what does that mean, right? We could look at, say, 30 years of data, right? And there's one day in 30 years that's 110 degrees in San Diego. So what happens if you size the system to that one day? That's extremely rare. It would be a really large, high power system, right? And now you can say, well, that's fine. I have enough power for that very hot day, and then I just use less power on other days. It's all fine. But the problem is actually equipment gets less efficient if you have a smaller, what's called a power factor. So if you plot the efficiency, and we could use now the COP as a function of what's called a power factor. Power factor is the actual power use divided by the rated power. And the COP goes actually up. I don't know the exact function, but it goes up to if you have a higher power factor. And so the rated COP that we discussed last time, that rated COP would be at a power factor of 1, which means that if you run your system at full power, that's the rated COP that you would read off from the inspection. That's the rated COP. Okay, so your system gets more efficient as it uses more power. Why is that? Well, you engineered the system to perform at that extreme condition, and that means that that condition it will be at its best. If you run it at partial load or small power factor, then it will be less efficient. Okay, so then let's think again. So would we use that one very hot day to size the system, 110 degrees in San Diego, once in 30 years? If you're wasteful, yes, you do that, right? Because you want to be cool on that one day, always cool. That's fine. But if you are a little bit energy conscious, you say, well, that would be just too extreme. I need big ducts. I need a big AC system. It costs more money to put in a big system, and so I can compromise a little bit. I'll maybe use the day that's the 1 percentile of the hottest day. So it means every year I will have 3 days where my system will not be enough to cool it. Or you could use the 0.1 percentile, right? So every day, every year you have 0.3 days where it's not enough. So you can basically make a compromise where you say, okay, I have a risk tolerance. I can tolerate that on some days it won't be cooling me down to 66 degrees. It may be 72 degrees on some hot days, but on all the other days of the year, I'll be fine. And so that's what's called the design day sizing. So on the
Let's see.
design day, this means that for every location, like San Diego or Imperial Valley, for Illinois, you have one temperature that you use. You plug in your model to then calculate what is actually the heat gain for that design day, and that's then the sizing of the system. So messy table. Don't worry about all the numbers here, but this shows you the different places in California. So the climate zone, the latitude, elevation, longitude, and so on. But what's important here is that we see the cooling design day, meaning that the temperature that you should use, the very hot day temperature, for different risk levels. So we have, if you want to have a 0.1, if you want to have a 0.1 chance that the temperature actually is higher, then you would size the system, San Diego, to 88 degrees. So you assume it's 88 degrees outside, you calculate your heat gain for 88 degrees, and then you use that to size the system. If you're happy with 2% of your days being too hot, then you can come down to 78 degrees. That means your system will be not much smaller now because you have a 10-degree difference, so the heat gain from the outside will be much less if you use 78 degrees versus 88 degrees. So that means as a designer, and certainly as a homeowner, you have that choice, and as a designer, you have a choice of which one you use.
So is it like the most efficient when you start seeing diminishing returns, like per Fahrenheit versus like
exactly.
temp per?
Yeah, so it's kind of a diminishing returns problem where you see, okay, if I go much smaller here, the temperature doesn't change much anymore because now many days are that hot, and so but if you go this way, you see a big jump happening in temperatures because it's very rare that we have 88 degrees in San Diego. Then of course, if you build a house in other places like San Francisco, you would then read off the temperatures for that place, and so there's databases out there from the Department of Energy that basically has all this data for all the places in the United States. So a building model like eQuest you're using that can then read the table from the database, and then you basically plug in your city, it reads off the right number, and then it sizes it for you. So all these data are available basically without even realizing that they're there because they're hidden in the database of the system. And the same, of course, for heating. So heating, we have here design dry bulb. Dry bulb just means that's the temperature we're designing for. And then you see for San Diego, it's 42 degrees if you're looking at a 0.2 chance of being out of luck. If you look at 0.6, then it's 44 degrees. So again, we're going to have a smaller heat loss for the 44 degrees number. So let's write that down. So we'll have size HVAC based on design days. Based on design days. With a certain probability of occurrence. Probability of occurrence. So e.g., for example, 0.2% or 1%. So 1% is 3 days, 3.6 days per year. So for 2% will be 0.7 days per year. So based on the probability, you will read off what is the temperature for that design condition. So the probability defines the outside temperature. For the design conditions. Then the outside temperature defines your heat gain or heat loss temperature defines the heat gain for summer and the heat loss for winter. Due to conduction and infiltration. And then the HVAC system will have to make up for that heat gain or heat loss. So the HVAC power rating and equals this heat gain or heat loss. Okay, so you define probability. Probability defines the outside temperature based on the table that we looked at. Outside temperature put into a building energy model will define the heat gain or heat loss. And then that heat gain or heat loss, that is the HVAC size that you would pick. Okay, now that's obviously too complicated for most people. So what happens if you go to the hardware store, you're buying an AC? What do they rate it by? What do they tell you what it's good for? They give you the power rating, but of course it doesn't mean anything to anybody. 10,000 BTU, right? So what did they say on the label? How do they define what the HVAC is good for? Yeah.
Doesn't it say like they do square feet?
Yeah, it's based on square feet of room size, right? So how can that be? We're doing all this should be. They're just using square foot of room size. How can that be a useful metric for giving you information about how much this HVAC could cool or heat?
Even if you have a less powerful HVAC, if you have a smaller room, it could deal with higher or lower temperatures more easily, just because it has to do it for less airspace.
Yeah, so in the room size, the argument that we discussed earlier comes in. A smaller room has less mass of air, so you can heat or cool it more quickly. So that certainly scales linearly with the HVAC size. But also, the room size comes in here because, as we know, the heat transfer is a function of the outside area of the envelope of the building. And so in this step, actually, the room size does come in because the heat gain is a function of the outside area. It's not exactly the room size, but room size is the only thing people know when they buy an AC. I have a 2,000 square foot home or a 1,000 square foot room. That's what you know, and so that's the only way to get people some information, some clue about what's the right size for their room. But of course, think about the manufacturer. Well, they want you to buy a bigger AC, right? It costs more, and they don't care how much you pay for energy, so they don't care about this. So when you're going to buy something, you should always undersize your system, because they're erring on the side of caution, so they're adding like 25% or something for making it too large. And so if you have a 1,000 square foot home and you see this AC can go up to 700 square feet, say okay, I'm fine. That's the right choice, because that's going to be more efficient. It's going to run continuously, be more efficient, and cost you less money during the operation. Yep.
Do they also assume that the size of your room that you want to heat or cool has like a reasonable design? And what I mean by that is, we can have the same volume but have vastly different surface areas of the envelope. So they assume that it's like a regular envelope size. Right. Yeah. As the question was, what do they assume about the room dimensions? Say the height versus width. This is a cube versus a thin rectangle. Yeah, they choose some typical room dimensions, which say 8-foot ceiling and so. Mm-hmm.
So when I was doing the homework or the project thing for house appliances and stuff, for my air conditioning system, it was rated in tons. It was like 2.5 tons. So how does that correlate with BTUs and all this stuff?
Yeah, the question was, air conditioning systems are rated by tons often and not by BTUs. So yes, for smaller systems that you buy for your home, like a through-the-wall system, you would see them in BTUs typically, but then the numbers get very large quickly. If you look at a whole office building, then it goes to tons. Don't know the exact conversion factor. I think it's 12,000 BTU is 1 ton, but I'm not 100% sure on that. Since I'm making mistakes all the time, I don't want to write anything down. But but yeah, it's a 1-to-1 conversion between tons and BTU. Okay, so that's how you size a system. So that's one important question, because when you buy it, when you design it, you really want to make sure you have enough power to be comfortable in your home while not using too much energy. But this really just tells you for that one day, everything is perfect, right? For the one hot day, everything is perfect. But it doesn't tell you, well, over the whole year, how much am I going to use? So what's the energy use over the year, over 10 years, that I'm going to have to pay for with the system. So the second step then is, after the sizing, is how do you actually estimate the operating cost? So operating costs. Estimation method. Alright, so now if you were in charge of doing that, how would you do this now? So you have your system size, so you have a 12,000 BTU air conditioner. How would you estimate the annual energy use, and then from that the annual cost of operating it? Well, you've already done it in the last few days if you started the design project. How does eQuest do that? How does eQuest come up with the cost that you get at the end? Just click the button, right? It happens automatically. So what happens under the hood? Well, eQuest has the temperature for every hour of the year. So that's what's called a typical weather year, a typical meteorological year, TMY. Typical meteorological year. So that means that, again, DOE does that. They actually take 30 years of weather data for every city, and then they figure out what's the most typical year that happened in those 30 years. And that means they take every month, say all the Januaries, they pick one January from one year, one February from another year, always the most typical one based on some computer algorithm. And then that's an artificial year that's based on real data for each month, but puzzled together in different ways, that forms the typical meteorological year. So one typical month times 12, drawn from 30 years plus of weather data. So one typical month is times 12 for 1 year is drawn from 30 years or more of weather data. And that makes sense because the weather affects how much we run this AC, right? San Diego, 72 degrees, 74 degrees, we don't turn it on. So those days will have 0 AC energy use. And then in September, we may have 80 degrees or 85 degrees. Now we do turn it on. So on those days, we'll have more energy use. So really, we need to understand for every hour of the year, is this equipment operated? And if it is operated, how much is it operated? And then we can estimate for the whole year by adding up every hour what the total energy use is for the entire year.
I assume in eQuest it has all this data, but you still have to input a temperature you want in the building, and then you can find the differences and do all the calculations.
The question was, in eQuest it has better data, but what about the inside of the building? And so yes, you're right, you have to input the inside of the building, what do you want, right? Because if you want an 80 degrees home, your AC use will dramatically be lower than if you want a 70 degrees home or 60 degrees home. So that makes a big difference, and that's what then you have to input as the designer. And then you say, well, I'm operating a gym. A gym needs to be very cool, so I'm putting in 60 degrees. Or I'm operating a sauna, then, well, I don't care. It could be 100 degrees, nobody cares. So that's something that depends on the type of building and your choice for that building. Okay, so then we use that data. We now simulate the building heat transfer. For 8,760 hours equals 1 year. So we simulate the building heat transfer for 8760 hours, which is 1 year. And then we sum it up. And then we get the annual cooling load. And of course also the annual heating load. So that's what you can do with eQuest. You can input your building, you run it, and then you can try out, well, what happens if I set my inside temperature to 80 degrees? What happens if I set it to 60 degrees? So that's all something you can play around with to find the right answer. Yeah.
Are the heating loads and cooling loads equal to each other?
Are they equal to each other? So the question was, are they both equal, heating and cooling loads? No, they depend on both what you want, inside temperature and the outside weather conditions. So basically in San Diego you have more cooling loads because it's warmer than in San Francisco, where you have more heating loads. So that's actually, they're not equal, so they can be very different. And of course in Alaska you may have no cooling load at all because it's too cold. Okay, so that's how people do it today. Now there's one tool or one trick we can use to estimate this. That's called the balance point temperature, which is part of the homework that's due on Friday. So let's talk about this balance point temperature concept. It will give us some intuition about what actually happens when we do this full analysis on a computer, where we really don't understand what's going on. So the balance point temperature can help to approximate the heating load, cooling load. So it's balance point temperature, or BP. Balance point temperature. So we're now trying to bypass this simulation, which in the old days was hard to do without computers. Today it's much easier with eQuest. Bypass this by using a different way of estimating the required annual heating and cooling load. So let's start with the heat gain or loss from the building. So we had said if you look at all the envelope, you look at all of the walls, the perimeter losses, then the equation is Q dot equals U times A times delta T. We use the heat transfer coefficient. A is the area of the envelope, and the delta T is temperature between inside and outside. Then we have heat gains. Inside the building. From internal heat sources. So that's our heat gain from equipment and from people. So like lighting, people in the room, and so on. So now what happens if those are equal? So here we have Q dot, and that is 3. don't have to invest any more money than we already do by generating this. We're already running these machines anyways. We're running the lighting anyways. So we're just getting free heat here. So if those two are equal, if internal heat gains are equal, to envelope losses, so Q3 is equal to that. So what happens if the internal heat gains are equal to the heat loss? What happens to the temperature in the building? Temperature will be constant, right? There's balance. If that's the case, then temperature is constant. Let's call this the Tn. Let's put the inside temperature. That's what we call the building is in balance. Building is in balance. That's what the name comes from. Yep.
And the Q3 doesn't. It's not any like. Not including HVAC systems. If nothing you include
Right.
that you're paying for to put heat
No.
or take heat out.
Yeah. So the internal heat gains are just the lighting, the people in the building, the equipment in the building. It's not about HVAC. Right? HVAC is separate. This analysis is kind of a pre-HVAC analysis. You're basically thinking about, could I heat this building just with the internal heat gains? Would that be enough to heat it? And the answer is yes. You actually wouldn't even need an HVAC system, right? The answer probably is not yes, but at least that's the concept we're trying to explore here. How does it work if we don't have an HVAC system? Okay, so if that's the case, if T is constant, then we can also write out this equation. So Q dot free equals then UA delta T. That delta T now we'll call a delta T star, because it's one specific delta T where we basically have just the right temperature difference for this internal heat gain to equal the outside. And so delta T star is then T3 minus T balance point. Sorry, T in minus T balance point. So delta T star equals T in minus T balance point. Okay, it'll make more sense if we look at the graph that we're going to plot now. So if we have here, let's graph the outside temperature. And here we have the heating, BTU heating, and BTU cooling. And then we draw a line here, straight line. Here we'll put 70 degrees Fahrenheit. That's our desired temperature inside. And this amount here are the internal heat gains. And this here, this point here is the TVP. That's the balance point. Okay, so we have the y-axis heating and cooling, BTUs. Then we have a temperature of the outside on this axis, and then we have this line here. This line tells us for a given outside temperature what will be the heating or cooling energy that we need to keep the building in balance. Let's look at these extreme points. So what's happening right here? So right here we have zero heating, zero cooling. No AC required, no HVAC required at all. It's colder outside. It's colder than 70 degrees. We like to have 70 degrees inside. That's the design. Inside temperature. So we like to be at 70 degrees. It's actually colder outside, but still we have no heating, no cooling. Why is that? That's because we're actually losing heat here, right? We are it's colder outside, so 70 degrees inside, 60 degrees outside. We're losing heat, but at that point we're making up for that heat loss with the internal heat gain exactly. So here, this point it's colder outside, but it's just cold enough that the internal heat gains are balancing the building. Whereas if it's 70 degrees outside, what happens with the heat loss to the outside? So 70 degrees inside, 70 degrees outside. Our delta T is 0. Okay. So now we have a balance in temperatures between inside and outside, but there's no more heat exchange between inside and outside. So what's happening now? Now we have to cool the building. Why is that? Same temperature outside and inside. Why do we cool the building? Because of the internal heat gains. We're adding heat to the inside, so we're putting the building out of balance. We're adding more heat even though it's already 70 degrees, and that additional heat now has to be removed through cooling the building. So this line basically tells us about how does the building behave for a given outside temperature. We can read off what we have to put in for heating and for cooling. So if the temperature outside is here, go down, this is the cooling load. Temperature outside is cold here, go up here, this is the heating load. So this tells us how the building works. Yeah, question?
So is the entire graph scaled to wanting 70 degrees Fahrenheit on the inside? Like,
Yeah.
okay.
So the graph is scaled to having a temperature on the inside that is your desirable temperature. Okay. So if you change that temperature, then the graph will change. Yes, let's think about how to change the graph. What actually is how can it be that this graph is valid for all buildings, right? That's impossible. So, the graph will change. The graph changes for one thing will change, will be different U times A. So if you have different area, different heat transfer coefficient, that will change the graph. Why is that? Well, the heat loss is a function of heat transfer coefficient and area. Right? So it must be that if you have a bigger building, or if we have a worse insulated building, then this graph must change. And how does it change? Well, it turns out that actually the slope of the line here is this slope here. Is delta Q over delta T, and that's U times A. So if you have a building that has a different u times a, the slope of this line will change. So this would be a building with a larger heat loss. This would be a building with a smaller heat loss. The other thing that may change would be the internal heat gains, right? You may have a building with a lot of people inside, or a building with just one person inside, or you have efficient lighting or inefficient lighting. So we also have changing in the internal heat gains, different internal heat gains. And that would affect how your line starts off. So what's the intercept of that line? So if you have 0 internal heat gains, then actually you would be in balance right here. So Q3 equals 0. And then the larger your heat gains are, the line will start further down. Larger internal heat gain. So larger internal heat gain if we move this way on these lines. Okay, so that's nice. That means that whatever building you have, you can calculate the internal heat gains. Like if you do an eQuest tells you, okay, I have so much lighting, I have so much equipment in the room, so many people. You can calculate the heat gain internally, and then you can actually draw this line to be at the right level. In the extreme case, you're avoiding cooling here because you don't have heat gains. You can actually survive in 70 degrees outside without cooling. The more heat gains you add, the more cooling you have to do to maintain your comfort temperature inside. Okay. And so in the last piece of the puzzle here, because so far we've just talked about concepts, we haven't really talked about numbers. So how do you calculate the annual energy use? So how to get from TVP, so the T balance point, to annual energy use. And here we use a concept that's called heating degree days and cooling degree days. So CDD, cooling degree day, and HDD is heating degree day. So how are those defined? So HDD, heating degree days, is defined as going from day 1 to 365. So over the whole year, we're summing up T balance point minus T out. We only add to that sum if balance point temperature is greater than T out. And for cooling degree days, it's a similar situation. Summing over the year. But now it's T outside minus T balance point. And we're only summing if the balance point temperature is less than T outside. And then finally, we have Q dot annual. The annual heat gain or heat loss is U times A times heating degree days. So heating, and then the same for cooling. Okay, so now it goes back to what we said about eQuest. At eQuest, you simulate every hour of the year, and you sum up all of the hours, and then you get the total energy use. Here, similar concept. Now we're looking just at the days. So we're looking at the daily average temperature, and we're figuring out for, say, day 1, what was the difference. Say it was January 1st, the outside temperature was 60 degrees. Looking at what's the balance point. Balance point may be 65. So if it's 60 degrees, we have so much heating we need to apply. Next day was 55 degrees, more heating. Next day was 65, zero heating. Every day we're adding up these numbers, and then we are getting an idea of, over the whole year, how many heating degree days do we have. So why that word here? It's days, because we're adding days, and degree days, because we're adding temperatures. So on one day we have 5 degrees, on the other day we have 10 degrees, so we're adding temperatures. So we're getting a metric that gives us both information about the length of time, the days, as well as the temperature difference on those days. Same for cooling, just the reverse thing, where we only count those if it's warm outside. Then if you look back at our big table, then we see that those numbers here are actually listed for every city too. So here, HDD, heating degree days, which means for every city in California, we now know, okay, San Diego has 1,500 heating degree days, which means that, say, if there was 100 days, on average it was 15 degrees too cold on those 100 days. That's 100 times 15 is 1,500. So that means that if we have San Diego, we can just read off these HDDs, plug it in here. This gives us information about our building, the area of the outside, the U coefficient, we get energy use. So that's another way, without a computer program, to quickly estimate energy use for buildings. So when we go to San Francisco, we see 3,000. So San Francisco needs twice as much heating energy because it has twice the heating degree days than San Diego. And then so here we have Salt Springs, 3,800, even more. And then some cities that are more south will have smaller heating degree days because you won't have to heat as much. So this gives one number that summarizes how good a climate is for heating and for cooling, and then how we can calculate energy from that. Okay, thank you.